Dear students, for today we'll see some error detection methods. So let's start with the topic error detection methods. And in these methods, we are going to see around 4 different methods of error detection where the error is detected by a particular process at the receiver stage. Now let's start our discussion starting with the basic thing. What is actually a communication error? A condition when the receiver's information does not match with the sender's information. During a transmission, digital signals suffer from noise that can introduce errors. This is important. When digital signals suffer from noise that introduces errors in the binary bits traveling from sender to receiver, that means a logic 0 bit can change to logic 1 or a logic 1 bit may change to logic 0. So as a whole, error is something, whatever we have transmitted from the transmitter at the receiver end, if that data, that message, that information doesn't reach properly, then there is an error. If the data sent is in binary form and if any of the bits are changed while receiving, logic 0 becomes logic 1 or logic 1 becomes logic 0, then there is a error occurring. There is an error occurring at the receiver stage. Okay. Then we'll go to see what do we mean by error detecting codes. Whenever a message is transmitted, it may get scrambled by noise or data may get corrupted. Okay, so whenever a message has been transmitted from transmitter to receiver, it may get scrambled by noise or it may get corrupted. Okay, to avoid this, we use error detecting codes, what we are going to do today. So to avoid this, we use error detecting codes, which are additional data added. Okay, in this process, we are going to add some additional data to a given digital message to help us detect if any error has occurred during transmission of the message. Okay, then with this, we will see the different error detecting methods. Now here, basic approach used for error detection is the use of redundancy bits, where additional bits are added to facilitate detection of errors. So our main thing will be at the transmitter stage, we are going to arrange some field. We are going to arrange the pattern of the bits such that at the receiving stage, we should be able to understand if there is an error occurring or not. So some popular techniques for error detection are, so these are the 4 techniques what we are going to see today. Number 1, vertical redundancy check, short form is VRC. Number 2, longitudinal redundancy check, short form is LRC. Number 3, cyclic redundancy check, short form is CRC. And number 4 is checksum. Okay. Now in this, the number 1 and number 2, that is VRC and LRC, are based on your parity code detecting technique. So number of ones in a given data will give you the parity, and a parity can be odd parity if the number of ones is odd, and it can be even parity if the number of ones is even. Okay, so the first two, that is the VRC and LRC, are based on your parity bit check method. Number 3 is cyclic redundancy check, where we are going to take the data, and that data will be divided by a constant number, and there you will get a remainder. The same process will be done at the receiver, and if the remainders match, the error is not there. If the remainders won't match, error is there. Okay. And the fourth method, that is the checksum, we are going to break down the complete data into some smaller modules, and we are going to add them, and after adding them, whatever sum we get, the same procedure we are going to do at the receiver. And even at the receiver, if you get the same sum for the data given, then there is no error. If the sum at the receiver differs from the sum at the transmitter, then the error is there in the data sending. Okay, so these are the 4 methods what we are going to see. So first we'll start with vertical redundancy check, VRC. So here, first we'll see the theory of VRC, and then we'll take an example where you will understand what is VRC. Okay. So if you see the theory of VRC, vertical redundancy check, VRC, vertical redundancy check is also known as parity check. In this method, a redundant bit, also called parity bit, is added to each data unit. This method includes even parity and odd parity. Even parity means the total number of ones in data is to be even, and odd parity means the total number of ones in data is to be odd. Example, if the source wants to transmit data unit, okay, say 11001111, this is what you want to transmit. Okay, so this is 11001111 using even parity. Okay, so we are going to use even parity to the destination. The source will have to pass through even parity generator. Okay, now here what we are saying is we are going to send a data. This will be our data 11001111, and we are going to follow even parity method, means even parity scheme here. So even parity will be followed here. Okay. So at the receiver, you accept the data with even parity, that is number of ones in the data. If it is even at the receiver, then the data will be accepted. If by any chance the number of ones in the data becomes odd, then the data will not be accepted. Okay. So here we can take this example and see here. So here you can see the data is, as told earlier, 11001111. So this is 11001111. This is the data. This is the data what the sender is going to send. So this is the sender who is going to send the data, and the data will go to a parity generator. This generator is going to generate a parity bit by counting the number of ones. So if you count the number of ones in the data, this is the first, this is second, this is third, this is four, and this is five. You have five number of ones. And because in this system, as we have told in the example, we are going to follow even parity, then 5 has to be made as 6 by inclusion of the parity bit. So one extra bit, whatever we are going to add here, will be logic 1, because this 5 plus this 1 will make the number of bits as 6, and 6 is an even number. So we are following even parity. So here ultimately what we are going to send is the data here 11001111. This is the same data what we are seeing here is the same data, and then this one is an extra bit which will be added by the even parity generator, so that number of ones in the complete code word here, the number of ones will be even. So if you check here, this is the first one, this is the second one, this is the third one, this is the fourth one, this is the fifth one, and the parity bit will be the sixth one, so it has even parity. So here you can see there are 6 logic ones in the code which is going to be transmitted to the receiver. It will be having 6 logic ones, so it is even parity. So that code will reach the receiver, and this is what has been reached here. So here you can see this has been reached to the receiver now, and in receiver is going to check the logic number of ones by the parity checker. So it will check logic number of ones. Now in this data, 1, 2, 3, 4, 5, 6 number of ones are there. Once it passes through a parity checker, it will tell that it is 6 number of ones. So it is even parity. If it is even parity, it will accept the data. If it is odd parity, it will reject the data and tell the transmitter to retransmit it. Okay, so this is how the system in VRC is going to work. So here you can see theory of it. A parity generator will count number of ones in data unit and will add parity bit. In the above example, number of ones in data unit were 5. Parity generator appends a parity bit that it includes a parity bit 1 to this data unit, making the total number of ones as 6, which will be clear from the figure what we have seen earlier. Data along with parity bit is then transmitted across the network. In this case, 11001111 will be the ultimate data, including the parity bit that will be transmitted. At the destination, the data is passed to a parity checker. the number of ones in the data is counted by the parity checker. If the number of ones is to be odd, like 5 or 7, the destination will come to know that there is some error in the data. The receiver then rejects such erroneous data unit, the data which is having error, and it will ask the transmitter to retransmit the data. But if the number of ones is even, like 4, 6, then the receiver is going to accept the data because it's even parity, and the system, as we told in the example, is going to run on even parity scheme, and then it will accept the data. Okay, but if the number of ones are odd, it is going to reject the data. Clear? Then we'll see what are the advantages and disadvantages of VRC. So first advantage is VRC can detect all single bit error. So it is good in detecting all single bit errors. It can also detect burst errors, that is data in set, but only in those cases where the number of bits change is odd. Because as in this example, we saw that we were following even parity system. So even parity system is there. If it is even parity, if even if the bits change in that even parity and ultimately the total number of ones is even, it is going to accept. But if you're following even parity and if the total number of ones is odd, then it has to reject. So it will have that advantage of getting the burst errors known in case of even parity, but in case of odd parity, it cannot do it. Okay. So in case of odd parity, it will find out the error. So it can detect error when the number of bits are odd, that is the logic number of ones in the data is odd, it can detect the error. But if the logic number of ones in the data set of data is even, in that case, it cannot detect burst errors. Okay. So a disadvantage will be the same again. The major disadvantage of using this method for error detection is that it is not able to detect burst error if the number of bits is even. As I've told earlier, if you're following an even parity system, then even if the number of ones what reaches at the receiver, if it is even, 4, 6, 8. So if it is even, it is going to accept the data. It will not see any burst error or any set of data error in that. If the logic number of ones are even, it will accept it. It will only reject if in that case, if the logic number of ones are odd. Okay. Then we'll go to see the next method, which is called as longitudinal redundancy check method, LRC. So if you see the theory for it, it is also known as a two-dimensional 2D a parity check. In this method, data which the user wants to send is organized into tables of rows and columns. A block of bit is divided into table or matrix of rows and columns. In order to detect an error, a redundant bit is added to the whole block, and this block is transmitted to the receiver. The receiver uses this redundant row to detect error. After checking the data for errors, receiver accepts the data and discards the redundant row of bits. Okay, so whatever extra bits you have added, that receiver will eliminate them, discard them, and receives only the message at the receiver. Okay, now this system also you'll understand if you follow an example for it. Okay, then we will take one example. If a block of data of 32 bits, okay, so if a block of 32 bits is to be transmitted, it is divided into a matrix of 4 rows and 8 columns, which is also known as shown in the figure, which is shown in the figure. So here you will be having 32 bits altogether, and those 32 bits we are going to form into 4 rows and 8 columns. So 4 into 8 is 32. So we'll see that. So here you can see this is the first data, second data, third data, and fourth data, whatever shown here. So here you can see this is the first 8 bits of data. Okay, that is 11001010. Okay, so that is taken here. You can see that is taken here. Okay, so it is 11001010. Okay, this is second bit of data. So this is 10101010. So that is taken here. You can see this, that is taken here. Then third is 11001100. Okay, so this is 11001100. That is taken here. You can see this. And the fourth data, 8-bit data, is 11100011. Okay, so that fourth is taken here. and this is the fourth data. Now this becomes a table. This is a table, whatever the data has been arranged in. Okay, and these are the rows. These are rows, row number 1, row number 2, row number 3, row number 4. 4 rows, and you have 8 columns. These are 4 rows now here, and these are 8 columns. 1, 2, 3, 4, 5, 6, 7, 8. So these are your 8 columns. So it has been arranged in rows and columns. So it's a table. So these are 8 columns. Okay. Now here, the LRC bit, what we are going to add now, and that is the extra data what we are going to send. That is the extra bits what we are going to send. It is not data, it is not information, but it is an extra bits what we are going to send depending upon the parity of the column. Okay. Now here, if you see in this first column, okay, in this first column, you can see you have 1, 2, 3, 4, 4 number of logic ones. So it is even parity. So the bit what we will add to this column will be 0. Okay. Now, if you see the second column here, if you see the second column, the logic number of ones is 1, 2, and 3. So we are having odd figure here, odd number of logic ones. So we will add one more 1 as an extra bit. So the total number of ones in this complete column becomes even. So 1, 2, 3, 4 number of logic ones will be there. Same will follow in the third column also. So in the third column, you can see there are 2 logic ones here. So it is already even. So if it is even, we don't have to add any logic 1 here. So we'll add a 0 bit. Then fourth column, you can see it is all 0, 0, 0, 0. So it is even number of ones. So there is no ones. So it is taken as even number of ones. Then you see the fifth column, it is there are 3 number of logic ones here, which is an odd figure. So we'll add one more 1 and make it even number. So you can, if you see the next column here, so you have only 1 logic 1. So again, it is odd. So we'll add one more 1 here and make it even. If you see the next column here, then we have 3 logic 1s here, and then it is an odd figure. So we'll add one more 1 here so that it becomes even. And if you see the last column here, you have only 1 logic 1, so it is odd figure. So we'll add 1 and make it a even figure. So this is an extra 8 bits what you are adding depending upon the parity of every column. Okay. So these extra bits will also go along with the data. Now this is your data. You see here, this is 8 bit, this is 8 bit, this is 8 bit, and this is 8 bit. This was your 32-bit data. So this was your 32-bit data. Okay, and this data will be sent along with the parity bit which you have generated looking at the columns and following even parity. So this will be added along with the data, and these bits will be sent to the receiver. Okay, now this will go to the receiver. Now the receiver will check the table, it will check the columns, and it will check the number of ones in the column depending upon what the parity bits we have sent. If everything matches, then the data is accepted. 32-bit data is accepted by the receiver. If it won't match, if the logic number of ones in the column are not according to the parity shown in the extra bits which have been sent along with the data, then the error is there, and therefore the data will not be accepted. Okay. So here in this matrix of bits, a parity bit, odd or even, are calculated for each column. It means 32 bits of data plus 8 redundant bits are transmitted to the receiver. Whenever data reaches at the destination, receiver uses LRC to detect the error in data. Okay. Then what is the advantage of LRC method? It is used to detect burst errors. So if the errors are not a single bit error, if they are in set, if there are a set of data which is in error, then it is this method is very good to detect those type of burst errors. Then a disadvantage is the main problem with LRC is that it is not able to detect error if 2 bits in a data unit are damaged and 2 bits in exactly the same position in other data units are also damaged. So we'll take one example here. So in this example, you see this is the data what we are going to send first. This is the data what we are going to send. So this is 110011010101. Okay, so this is the first unit and this is the second unit. Okay, and this is what we will receive. Okay, so we will see it in a figure. So if you see it in this figure, the sent data was here. So on top you can see the sent data. This is the sent data and this is the received data. Okay, so this was the first unit, unit 1, and this was the second unit, unit 2. Okay, now here in the first unit, the first digit 1 has been changed to 0, and the last unit 1, this bit has been changed to 0. So there are two changes in the first position and in the last position of the unit. Even here, if you see in the second unit, the first position will be changed to logic 1. Okay, and the last position is changed to logic 0. Okay, now there are two changes made in each unit, but this will not be understood by the system. It will take the one change. Okay, so because it will go with the parities of the column and the two positions changes, it will not be accepted, and it will see that it takes it at one position only. So here, if you see, the main problem with LRC is that it is not able to detect error if two bits in a data unit are damaged and two bits in exactly the same position in other data unit are also damaged. So in such cases, it is not able to detect the error. Okay. So then we can also see the difference between VRC LRC. We can have some points which can give the difference between the VRC method and LRC method. So here the first column shows VRC method and the second column shows the LRC method. So in VRC method, the first thing what we have shown is VRC stands for vertical redundancy check. And similarly, the first point for LRC, it stands for longitudinal redundancy check. Okay, so it stands for longitudinal redundancy check. The second point in this redundant bit parity is added to each data unit in VRC, whereas in LRC, in this redundant row bits is added to the whole block. Okay, so here you can see that the row is added to the whole block. Then third point, VRC can detect single bit errors, whereas LRC can detect set of data that is burst errors. VRC is also known as parity checker. LRC is known as two-dimensional parity checker. Okay. Then here the advantage of VRC is that it can check all single bit errors, but can check odd parity only in the case of change of odd bits. This is what we saw the advantages. The advantage for LRC over VRC is that it can check all the best burst errors, even if it's odd or even. Then sixth point, it is not capable to check burst errors in case of change of bits is even, as we have told earlier, in the disadvantage of VRC. So similarly here, if you see if two bits in the data unit is damaged and also in other data unit, the same bits are damaged at the same position, then it is not capable of detecting such kind of error. That was the disadvantage of LRC. So these are the few differences of VRC and LRC. Then we'll go to see the next method, which is called as cyclic redundancy check, CRC. CRC is a different approach to detect if the received frame contains valid data. This technique involves binary division of the data bits being sent. The divisor is generated by using polynomials, that is, depending upon the position of the number of logic ones. The sender performs a division operation on the bits being sent and calculates remainder. Before sending the actual bits, the sender adds the remainder at the end of the actual bits. Actual data bits plus the remainder is called a code word. The sender transmits data bits as code words. So this concept also you'll understand once we take an example here. Then at the other end, that is the receiver, performs the same division performance operation on the code word using the same CRC divisor. If the remainder contains all zeros, the data bits are accepted. Otherwise, it is considered as there is some data corruption occurred in the transmission. Okay. So what exactly this procedure is, you can understand with this example here. So here we'll take an example. So let our data bit will be 11001. Okay. So this is our data, what we want to send from transmitter to receiver. So this is your data bits. So this we have marked as database. This is what we are going to transmit from transmitter to receiver. So looking at the position of logic ones, this is the zeroth position, this is the third position, this is the fourth position. Looking at the polynomial, there will be a divisor generated, and this divisor here is shown as 101. So we are going to divide this data by 101. So by 101. So here you can have a division process. 101 multiplied by 1 will give you 101. Okay, now here if you see 0 minus 1 is 1, then a carry over 1 minus 1 is 0, 0 minus 1 is 1, and 1 minus 1 is 0 here. So here this 0 you can take down. Okay, and then again you can multiply 101 by another 1, and you can get this 101 here. So if you see this 2, 0 minus 1 is 1, then 1 minus 0 is 1, okay, and 1 minus 1 is 0. So this last one will be taken down here, 1, then again 101 into 1 will be your 101, and then if you do this subtraction here, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0, so you will get remainder as 10. So this will be your remainder, which will be your CRC code. This is the remainder. Now this remainder will be added with the data and sent as a code word to the receiver. So here you can see your data was 11001. So that data is here 11001, and then this remainder you are adding again here at the last. So this is the remainder what you are going to add. And now this complete code word, you again divide it by the same divisor 101, what you have done in the transmitter. So our divisor is same here. Then again you follow the process 101 into 1 will be 101 here. And then you do subtraction. What remains is 110. Again 1011, saying again you do subtraction, you will get 111. Again 101, again you do subtraction, you will get 101. Again you go with 1, again 101 into 1, then you will do the subtraction here, you will get answer as 000. If the answer, when you divide the complete code word, that is data bits plus the remainder, data bit plus the remainder with the same divisor, if the remainder here comes as 0, then there is no error, data is accepted. But if the remainder is existing, then there is an error and data will not be accepted. Okay, that means the same division process, whatever you have done at the transmitter to find the remainder, you have done here with the complete code word. And ultimately, when you add the remainder with the actual data, the remainder for that particular process should come 0. So if it is coming 0, then there is no error, data is accepted. If it is not coming 0 in the receiver, the last remainder, then there is an error. Okay. Then what are the advantages of this cyclic redundancy check? So here, this is just a simple code and can be produced and implemented in any form of applications. Easy to view single bit errors and multiple burst errors. It is based on the severity and complexity of the error. The error correction mechanism can be generated. This type of mechanism is commonly found in file repairing software and utilities. Because of its simplicity, it can fit any type of operating system and all versions, including the latest. Then what are the disadvantages of CRC? Though the cyclic redundancy check looks like an authentication mechanism, it is not a trivial and easy to crack mechanism. It is not suitable for security purpose. Without the error correcting mechanism, using CRC alone will be a useless thing. So these are the disadvantages of CRC. Then we'll go to the next method of error detection, which is called as checksum. This is a block code method where a checksum is created based on the data values in the data blocks to be transmitted using some algorithm and appended to the data. Then it will be included with the data. When the receiver gets this data, a new checksum is calculated and compared with the existing checksum. A non-match indicates an error. If it matches, there is no error. So this method also will understand if we take an example for it. So in a checksum error detection scheme, the data is divided into k segments, each of m bits. say you divide your bigger data into 4 segments or 5 segments, each of 8 bits. So you can say that you have divided it in k segments, each of m bits. In the sender's end, the segments are added using ones complement arithmetic to get the sum. Now, when you say ones complement arithmetic, that is whenever you add two things, and if there is a carry generated, the carry will be added for the next addition. Say, for example, here, if I show you what is ones complement. So here, if you're adding 1, 0, 0 plus 1, 0. Okay. So if this is the addition, then 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, carry is 1. So this carry will be added next here. So next what addition you do is 0, 1, 0, whatever your answer was, plus 1. So this will be 1, 1, 0. This will be the answer of the addition of these two. Okay. So this is called as ones complement arithmetic to get the sum. The sum is complemented to get the checksum. The checksum segment is sent along with the data segments. At the receiver's end, all received segments are added using ones complement arithmetic to get the sum. The sum is complemented. If the result is 0, the received data is accepted, otherwise it is discarded. Now this thing will be very clear to you if you see an example. So here, once a complement arithmetic, what we are going to use in this method is while adding two numbers using one's complement arithmetic, if there is a carryover, it is added to the sum. As I have told you earlier, so we have taken this example. So 1, 0, 0 was added with 1, 0, 1. Say now this is a 0 plus 1 here. It is 1, 0 plus 0 is 0, 1 plus 1 is 0, carry is 1. Now this carry will be taken and added to this here. Now here if you see 1 plus 1 will be 0, carry is 1, so 1 here and 0. So this will be the ultimate answer. Now this type of process is called as ones complement arithmetic. Okay. Then we'll see an example. So here we'll have a original data. So this is your original data, which is divided into 4 blocks, which is divided in 4 sets here. So if you see the set number 1, this is your 8-bit data. If you see the set number 2, this is your 8-bit data. If you see set number 3, this is your 8-bit data. If you see set number 4, this is your 8-bit data. Okay. Now that means there are 4 sets. So k is equal to 4. And in every set there are 8 bits. So m is equal to 8. Okay. So at the sender, first we will add the first and second set. So the first set is here. Second set is here. We are going to do the addition. Once you do the addition, 1 plus 0 is 1, 0 plus 1 is 1. So 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry is 1. So here, this is a simple addition, whatever you have done, but you have got a carry. So to this sum, whatever you have got here, you have to add that carry 1. So then it will be called as your method of ones complement arithmetic, what we have seen here. Okay. So that 1 will be added here, and then you will get a sum like this. Okay, then you add the third set of data. This is your third set of data. You will get this sum. Okay, then you add the fourth set of data. You will get this sum. Now in this addition, you are again generating a carrier. That carry will be again added and you will get a sum here. This will be the sum of all the 4 sets, whatever you have added. Okay. Now that sum, you make it one's complement. So 1 will become 0, 0 will become 1, 1 will become 0, 0 will become 1, 0 will become 1, 1 will become 0, 0 will become 1, 0 will become 1. Now this complement, this is your checksum. This is your checksum, what you have got. Okay. Now at the receiver, you do the same procedure. You take the data, first data, you add it to the second data. There will be a carry 1 here that will be added here. That sum will be added with your third set of data, and then you get this sum. Okay, and that will be added with your fourth set of data. Okay, then you will get a sum here, and that sum will come with carry here, and that carry will be added here, this carry. Then you will get this sum. Okay, this sum as we have got it here. Okay, and then you complement it, you will get this sum here. Okay, now when you sum up them, when you sum up the actual sum and the complemented sum, you will get all sum as 1 1 1 1 1 1 1. Okay, and then if you complement that, you will get all 0 0 0 0 0 0 0. This will be the procedure what will be done at the receiver. And if this last stage shows you 0 0 0 0 0 0 0, all zeros, then you have to accept the data. If it is not showing all zeros, then there is an error. You cannot accept the data. You have to reject the data. Okay. Then what is the advantage of checksum? The checksum detects all the errors involving an odd number of bits as well as the error involving an even number of bits. And what is a disadvantage? The main problem is that the error goes undetected if one or more bits of a subunit is damaged and the corresponding bit or bits of a subunit are damaged, and the corresponding bits of opposite value in second subunit are also damaged. This is because the sum of those columns remains unchanged. So ultimately, if the sum of those sets of data remains unchanged, error will not be detected. Okay, whereas the data has been damaged. So that is the disadvantage of this checksum method. Okay. Thank you, students.